Hey everyone, and welcome. Today we're going to talk about something so basic, so fundamental, that we almost never think about it: measurement. But really, it's the invisible framework holding up our entire world, from global trade to the phone in your hand. It's the language of science. So, how did we all get on the same page?
No, really, just think about that for a second. How did billions of people across all these different cultures and countries agree on the exact length of a meter? It sounds simple, right? But the story of how we got there is this incredible journey, a quest for a universal, unshakable standard.
So, here's our game plan. First, we're going to jump into the history, from using actual feet to using the speed of light. Then we'll take apart a measurement system to see what makes it tick. After that, we'll look at the different tools we have, and finally, we'll talk about how we make sure those tools are actually telling us the truth. All right, so to tackle that big question about the meter, we have to start at the very beginning. Because before you can measure anything, everybody, and I mean everybody, has to agree on the ruler. You've got to have rules for the game.
You know, way back when, measurement was personal. A foot was, well, it was literally the length of the king's foot. A hand was used to measure how tall a horse was. And for a small village, that kind of works. But you can imagine the problem, can't you? If you're trading cloth with the next town over, and their king has smaller feet, you've got a problem. It was messy, it was imprecise, and it was a total nightmare for any kind of serious trade.
The meter's evolution is the perfect example of this search for something better. We started with this grand idea: let's base it on the size of the Earth itself. A noble goal, but turns out measuring the planet isn't exactly a weekend project. So we moved to something much smaller, much more manageable: the very specific wavelength of light given off by a krypton-86 atom. Better, but still not perfect. The final leap, where we are today, was to tie it to a fundamental constant of the universe: the speed of light. It's beautiful, it's elegant, and it means anyone, anywhere in the cosmos with the right tech could figure out exactly what a meter is.
So this whole quest for standards leaves us with two main systems today. You've got the imperial system, your yards, feet, and inches. It's got a lot of history, but the math is, well, it's a bit of a headache. There are 5,280 feet in a mile. Why? Who knows? And then you have the metric system, the SI. It's built on this brilliantly simple idea: everything is based on powers of 10. A kilometer is just 1,000 meters. A centimeter is 100th of a meter. It just makes sense, which is why it's the standard for pretty much all of science and most of the world.
Okay, so we've got our rules, we've got our units. But what actually happens inside a device when you take a measurement? It's never just a number that magically appears. It's the final step in a whole chain reaction. So let's look at the blueprint for how that works.
It sounds complicated, but almost every measurement system, from a simple thermometer to a complex satellite, follows these 5 steps. Let's walk it through. Imagine a digital thermometer. Step 1, the sensor at the tip feels the heat. That's the primary sensor. But heat isn't electricity, right? So step 2, the variable conversion element, turns that heat information into a tiny voltage. That signal might be weak or have some noise, so step 3, the signal processor cleans it up, maybe boosts it. Step 4, that clean signal is sent along a wire, that's transmission. And finally, step 5, it hits the presentation element, the little LCD screen that shows you the final number. From sensor to screen, every single time.
Now, when an engineer has to pick a tool for the job, it's not just about grabbing the most expensive, top-of-the-line gadget. It's always a balancing act, a trade-off between 3 big things. First, performance. How good does this thing really need to be? Then, environment. Is it going to be in a quiet, climate-controlled lab or out on a vibrating, scorching hot factory floor? And finally, there's always cost. Not just what it costs to buy, but what it costs to keep it running.
Okay, so we know we have to make choices. So what are the options? Let's open up the toolbox and check out the main categories of instruments we have to work with.
The first big difference is active versus passive. A passive instrument is basically self-powered. Think about an old mercury thermometer. The heat it's measuring is the only energy it needs to make the mercury rise. Simple. But an active instrument needs some extra juice: a battery, a plug in the wall. A perfect example is the fuel gauge in your car. It uses the car's electrical system to read the level in the tank. Active instruments can do more complex things and often give you a much more detailed reading.
Next, we've got deflection versus null type. Now, a deflection instrument is probably what you picture first: a needle on a dial, a pointer moving across the scale, like on a simple bathroom scale. It just deflects to show the value. But a null-type instrument is way cleverer. Think of a classic 2-pan balance scale. It doesn't just measure the weight, it actively balances your unknown item against a set of known, precise weights until they're perfectly equal, or nulled out. Because they're always comparing to a known standard, null-type instruments are usually way more accurate. And this brings us to a huge one, especially today, analog versus digital. An analog signal is smooth, it's continuous. Think of that liquid in a thermometer. It can stop at any infinite point along the glass. A digital instrument is different. It thinks in numbers. Its output jumps in discrete steps. It's either 21 degrees or 22 degrees, nothing in between. And while analog might feel more real, the massive advantage of digital is that it speaks the language of computers, which is why it's taken over the world.
So, we've got our rules, we've got our toolbox, but how do we know if our tools are any good? More importantly, how do we keep them good? This brings us to the final and maybe most crucial section, the performance check.
The absolute bedrock of performance is accuracy. It's a really simple idea. How close is your answer to the real answer? If it's truly 20 degrees outside and your thermometer says 20.1, hey, that's pretty accurate. If it says 25, not so much. This is the whole point of measuring in the first place, getting close to the truth.
But here's where people get tripped up, because accuracy is not the same as precision. The classic way to think about this is a dartboard. Imagine you throw a bunch of darts. If you have high accuracy but low precision, your darts are all over the place, but they're scattered around the bullseye. Your average is good, but you're inconsistent. Now, what if you have low accuracy but high precision? That means all your darts are in one tight little clump, but it's way over in the corner of the board. You're very consistent, but you're consistently wrong. What you want, the goal, is high accuracy and high precision. A nice, tight group of darts right in the center of the bullseye.
Okay, besides those two big ones, there are a few other terms you'll see. First is sensitivity. Basically, how responsive is it? A super-sensitive scale will show a change even if you add a single grain of rice. Then there's resolution. This is the smallest step the instrument can actually show you. Your digital kitchen scale might have a resolution of 1 gram. It literally can't show you half a gram. And then there's a weird one called hysteresis. This is when you get a different reading going up than you do coming down. You see this in old thermostats. It turns the heat on when it drops to 19 degrees, but won't shut it off until it climbs up to 21. That gap, that's hysteresis.
Now here's the kicker. No instrument stays perfect forever. It's just a fact of life. Little bits of wear and tear, temperature swings, you name it, they all cause the instrument's performance to slowly drift away from what's true. The scale that was perfect last year might be off by a little bit today.
And that is exactly why we have calibration. You can think of calibration as a tune-up for your measurement tools. It's the process where you check your instrument against a standard that you know is correct, and then you adjust yours to match it. It is, without a doubt, the most important thing you can do to make sure your measurements are accurate over the long haul.
All right, let's wrap this up. What are the big ideas to take away? First, we need standards, like the SI system, so we can all speak the same measurement language. Second, every measurement is actually a system, a chain of events. Third, there's a whole toolbox of different instruments out there for different jobs. And finally, and this is the big one, all the accuracy in the world doesn't mean a thing if you're not doing regular calibration to keep it that way. So I'll just leave you with this one question to think about. From the GPS that got you here to the Wi-Fi that's streaming this right now, our lives are running on a hidden foundation of millions of measurements happening every second. What's something in your world that's working perfectly right now, all because of a measurement you never even see? Think about it. Thanks for listening.